Good morning, everyone. Welcome back. We're going to finish off the current handout, which is Physics 30, the rest of the story, part 1 today, by finishing the final lesson in that handout, which deals with refraction of light. This lesson can be found on page 18 of the lesson handout. And you did study refraction a little bit last year in Physics 20. You learned about mechanical waves undergoing something called refraction. Well, we're going to go into refraction in a lot more detail today, and then we're going to start applying it to light and electromagnetic radiation as opposed to just mechanical waves. So mechanical waves undergo refraction, this is the word we use, when they travel from one medium to another medium. So for example, when a water wave travels from a deep part of a pool to a shallow part of a pool, it undergoes something called refraction. When you have a wave on a spring that travels from a very, very thin spring to a very heavy spring, it will undergo refraction. So what's key here is that the wave changes the medium that it's traveling through. And it turns out that light, even though it's not a mechanical wave, as well as all forms of electromagnetic radiation or waves, also can refract, and do refract when they travel from one medium to another medium. So when refraction occurs, there are a number of things that change. One of the things that changes is the wavelength. One of the things that changes is the speed. And the other thing that can change and usually changes is the direction of motion. And I will tell you right now that if the wavelength of the wave, when it undergoes refraction, gets longer, then the speed will get larger. If, when refraction occurs, the wavelength of the wave gets shorter, then the speed will get smaller. So whatever happens to the wavelength happens to the speed. And we'll worry about the direction of the motion in a little bit. What we're looking at here is quite honestly a visual that if you stare at for too long, it makes you a little ill. At least it does for me. There's all kinds of optical illusions going on in this thing. But what we are looking at is a wave traveling from a medium of low density to a medium with a high density. Now, we don't need to worry about what the specific substances are. It really doesn't matter. Basically, if you have a medium or a substance or a material and it has a high density, then what that means is it takes the wave longer to travel through it. The wave travels slower. And this is going to be a little difficult for you to see, but if you were to take a look at any one of these lines that are moving on the left, and I would normally point to them, but that's no good here, and you watched how fast these lines are moving up and at an angle, and then you looked at some of the lines on the right, you would discover that they are moving slower. So this is one of the things that you want to learn here, is that when a wave goes from a low density to a higher density medium, it slows down. And by the way, where the arrows are pointing, the low density is anything to the left of that solid line. And the high density is anything to the right of that vertical solid line. That solid line, by the way, is called the interface. And it's sometimes referred to as the boundary. The dotted line in the middle is called the normal line. In mathematics and science, the word normal means perpendicular to. So the normal line is a perpendicular line to the interface or boundary separating the two media. Now, a couple of other things. The lines that you are looking at that are moving can be thought of as being ripples. And they're what you would call in physics 20 wave fronts. The red line that is straight and then changes direction is called the wave ray. So there's a lot going on in this diagram. Now, I'm going to explain to you why the wave changes directions. When you take a look at the red line in this diagram, it's showing you the direction that the wave is traveling before it refracts and after it refracts. This is an analogy that was given to me over 30 years ago in a university course, and a prof said, let's imagine that instead of having a wave, what we have is a very long axle. And at each end of the axle is a wheel that's rotating. So rather than having the wave move in the direction of the red line, what we have is an axle that is rolling. And instead of having medium 1 and medium 2, we're going to say that this is pavement. Everything on the left is pavement, and over here on the right, this is very thick, like a foot thick mud. And we're going to start this axle rolling. Now what's going to happen is at some point the axle will be in this position. It's rolled along that red line and now it is at this position. And what you notice is that the wheel at the bottom of the page hits the thick mud first. And as a result, it's going to start moving slower. And if you stop and think about what's going to happen to the whole axle, if this wheel is moving with a particular speed, but the top wheel is moving faster because it's on pavement, that whole axle is going to start to pivot. The top end of the axle will be moving faster, so the whole thing will rotate clockwise. And then the result is going to be that when it finally gets into the mud, it will be traveling at a twisted angle. Now this analogy only goes so far, and it's not a perfect analogy, but it gives you an idea of what's happening in general to the wave. The leading part of the wave gets slowed down first, and it falls behind, so to speak. And the part of the wave at the top that hasn't yet refracted starts to move faster in relation to how fast the bottom is moving. So you get this twisting action. I'm also going to explain now why the wavelength decreases. When you take a look at how far apart the ripples are in the pavement, the ripples in the pavement are pretty far apart. They're certainly further apart than the wavelength in the thick mud. The ripples are closer in the thick mud, so the wavelength is smaller. Now, by the way, we already know that the wave will travel slower on the right. But now what we want to do is explain why the wave has a shorter wavelength on the right. And I'm going to go back in time to that same prof and explain her analogy that she gave me. She said, let's imagine instead of having a bunch of ripples or wave fronts, what we have is a bunch of people marching. This is a marching band. I just realized there's a person in the top right corner. I don't know who that is or why they're not involved. I guess they showed up late. So you have these rows of people marching in the direction of the red line. And each of these blue dots is a person. Well, let's just imagine for a second that you and I are involved in this, and that this green dot is you, and this green dot is me. And we're not going to use pavement and mud. We're going to use pavement and 1 foot of water. And if you've ever walked in a pool of water, you realize that it really slows you down. So what's going to happen is right now you and I are separated by a particular distance. But then a short time later, you will be here and I will be here. So now we've moved forward. This is you. This is you. And this is me. But I've hit the deep water. And as a result, my speed is going to decrease as soon as I hit the water, but your speed will not decrease. You're going to continue to move just as fast as you were. So imagine that you're walking behind me, you're marching behind me at a certain speed, and you're going to keep that speed going, but all of a sudden I slow down. The result is that we're going to get closer together. And by the time we get, I'll throw in a third point in time here, by the time we get into this position, where this is you, you're still behind me, where this is you, and this is me, we are closer together now than we were to begin with. So that gives you kind of a visual of why the wavelength decreases. So the speed decreases because the medium is just more dense. The direction changes because that axle rotates as the leading edge gets slowed down first. And the wavelength decreases because the leading edges are moving slower, so the ripple that is behind the first ripple that hits will catch up to the ripple in front of it. And there's an awful lot going on here with refraction of mechanical waves. The frequency is not affected by refraction. And I'm going to explain why that's the case. But I need to go back and review how waves are created. And we're looking right now at what's called a transverse wave. And it's not a very good diagram of a transverse wave because you don't see a whole wave, you're just seeing pieces of it. But I'll get to that in a second. If we were to try to look at the bigger picture here, everybody, there is a peak that travels along here. And this is what wave energy is. It's the peak of the wave traveling left to right. So if you kind of squint your eyes and you focus on a peak that starts over here, you can see that the peak is moving left to right. You have energy traveling left to right. But what's really happening is the substance itself is vibrating up and down. And I have a better visual here for that, which is this one. And you don't see the pieces of the wave moving up and down. What you see is definitely something moving left to right. But if you focus on any particular place of the wave and you block out everything else, in that particular part of the wave, something is traveling up and down and up and down. Now, why do we get this nice symmetrical pattern? The explanation to that, and I'm going to ask you to focus on the red dot in the middle here, is that every piece of the medium is going to vibrate with the same frequency because every piece is connected to every other piece. Over here on the left, everybody, we have a source. There is something taking that first piece of the medium and moving it up and down. And that first piece of the medium is connected to the second piece of the medium. So if I vibrate that first chunk of the medium with a frequency of 0.5 hertz, and it's connected to the second piece must also oscillate at 0.5 hertz. If I ask you now to go back and look at that red dot in the middle, why is it oscillating at half a hertz? Because it's connected to the dot to its left, which is oscillating at half a hertz. Why is that dot oscillating at half a hertz? Because it's connected to the dot to its left, which is oscillating at half a hertz. And since these are all connected and traced back to the source, we come to this conclusion. The frequency of a wave is determined by the source of the wave. It's got nothing at all to do with what the wave is traveling in. So we're starting to put this all together now. During refraction, the wavelength and speed both change, the direction changes, but the frequency does not. All right, well, it turns out that everything I've talked about here in terms of mechanical waves, I've explained by using physical substances. mud, objects that are tied together with strings, pavement. I've used physical ideas here to explain refraction, but it turns out that light, which has no physical substance to it, it's not a mechanical wave, light also undergoes refraction when it leaves one medium and enters a second. When light travels through a substance, we can predict its behavior by looking at something called the index of refraction of the substance. And the index of refraction of a substance is a number. It's given the symbol n. And it's really giving you a measurement of the optical density of the substance. So substances with larger indices of refraction are very optically dense, which means that when light is traveling in a substance with a large value of n, it travels quite slowly. And we'll talk about those numbers in more detail in a second. If light travels from a less dense medium to a more dense medium, then the wavelength and speed will both decrease and the light will refract toward the normal line. Okay, in the original video and also in your handout on page 18 of the handout, there was a serious mistake, and I also repeated the mistake verbally when I was explaining this in the video. What you're looking at the bottom of your viewing screen right now is definitively the case. When light travels from a more dense to a less dense medium, the wavelength and the speed will both increase and the light will refract away from the normal. That is correct now. I apologize for my mistake. I hope it didn't cause you too much confusion. So what we're looking at, everybody, is, as an example, when light travels from air to glass. It's traveling from a less dense to a more dense. When light travels from glass to air, it's traveling from a more dense to a less dense. That's a specific example, and the reason why I'm choosing those examples is I would like to show you a video demonstration right now of what it means to say refracting away from the normal or refracting toward the normal. So we're going to take a look at a video right now, and then we'll come back to the handout. All right, everybody, I'm going to show you two quick demonstrations here involving the refraction of light. You've been told that when light goes from one medium and enters a more dense medium, like for example going from air into glass, you've been told that the light will slow down, its wavelength will decrease, and it will bend towards the normal. Well, we're going to look at what that means to say the light bends towards the normal. You've also been told that if light were to go from a more dense medium like glass and travel into a less dense medium like air, then the light will speed up and the wavelength will increase and it will refract away from the normal. The main purpose of this demonstration is for you to see what refraction of light looks like and for you to understand what toward the normal and away from the normal means. So I have an acrylic block of glass here. It's a type of acrylic glass. It may not look like glass because it's black in appearance, but it's only black in appearance because glued on the back of it is a magnetized film, which allows me to stick this thing to the whiteboard at school and do demonstrations. If you look at the edge of it, you can see that it is definitely glass. You can see through it. Now I also have drawn on the surface that we're working on a dotted line. That dotted line is called the normal line. And in mathematics, the word normal means perpendicular to. And what this normal line is perpendicular to is the surface between the air and the glass. And this surface between the air and the glass is sometimes called the interface or the boundary. Now, I also have a little piece of plastic which I'm just going to put up here. Because you can't see the normal line through the glass, I just took a piece of plastic and I drew a bunch of dotted lines on it so that we can imagine we can see the normal line. And I also have a light source. I'll turn the light source on. You can see the beam of light, but you can't see it that well. And the reason why everything, by the way, is a little washed out and we have all these shadows is I'm lighting things up with an external light source right now to keep my camera in focus and to explain all of the pieces of what we're talking about here. So the first demonstration is a beam of light is going to go from the air and enter this block of glass. I'll turn the external light source off, and there are a number of things we don't care about in this demonstration. This beam of light that you're looking at where the pen is pointing is just a reflection of some of the light that's leaving the light source. There's also this smearing of light on both sides of the light source, and we don't care about that. We want to focus our attention on this bright beam of light which is leaving the light source, and that bright beam of light is in the air, and it's called the incident beam of light. The incident light is always the light in the first medium, and we're going from air into glass. And that means that this beam of light, the beam of light inside of the glass, is called the refracted beam of light. So we're going to focus on the incident beam of light, which is indicated here, and we're going to focus on the refracted beam of light, which is the bright beam of light inside of the glass. We don't care about this light over here. This is just the light after it goes back into the air from the glass. Now, what we want to pay attention to is the angle between the incident and refracted beams of light and the normal line. So if I look at this angle in here, this is the angle between the normal line and the incident beam of light, and that is called the angle of incidence. If I take a look on the other side at the angle between the refracted beam of light and the normal line, that is called the angle of refraction. And I hope you can see that the angle of refraction in this case is smaller than the angle of incidence. And what that means is the light refracted toward the normal. If I were to put a pen down on this and hold it in the same direction as the incident beam of light, you can see that had the light continued in that direction, it would have ended up over here someplace at the tip of my finger. But because it ended up here, what we say is it refracted towards the normal. And that's where that expression towards the normal comes from. So when you have light going from a low density medium like air into a high density medium like glass, it will slow down, the wavelength will decrease, and it refracts towards the normal. All right, this time what we're going to be looking at is a beam of light that goes from a high density medium, glass, into a low density medium, air. So this time we're going from glass to air. And I've got my light source pushed right up against the glass, which is where the light is going to start, so that when I turn the light source on, the light will essentially already be in the glass. And that means that the beam of light we look at in the glass should be called the incident beam of light. And when the light leaves the glass and refracts into the air, that beam of light will be called the refracted beam of light. And if you were to measure the angle between the refracted beam of light and the normal line, that would be called an angle of refraction. And if you were to measure the angle between the incident beam of light and the normal line, that would be the angle of incidence. I've turned my external light source on one more time just to get my camera to pull focus on everything. I'll turn on the light source now, and I will turn off the external light source. And just looking at this, don't forget that my pen right now is pointing at where we would measure the angle of refraction, and my pen here is indicating the angle of incidence that we would record. And if you take a look at what happens here, the angle of incidence has a certain value. I might estimate it to be 30 degrees. It doesn't matter. If I were to look at a 30-degree angle over here, a 30-degree angle here would be approximately in the direction of my pen. In other words, this is the direction the light would travel if it didn't change direction when it left the glass. And since the beam of light is pushed further away from the normal than where my pen is, that is where we get the expression refracts away from the normal. So when you have light traveling from a more dense to a less dense medium, from glass to air, it speeds up, the wavelength increases, and it refracts away from the normal, and that's what it looks like. If I wanted to refract towards the normal, just to review this, I could put the beam of light here. This now becomes the angle of incidence, and the angle of refraction is over here, and this is refracting towards the normal. So hopefully that gives you a better idea of what it means when we say that light refracts away from the normal or light refracts towards the normal. So let's draw what we saw. We saw that when the light was in air and then it reached the boundary and traveled into the glass, it refracted towards the normal, so that's what it looked like. On the other hand, when the light was in the glass, when it hit the interface, it ended up refracting away from the normal. And I want to label a few other things on here so that we have a record of it in our notes. I know I talked about it in the video, but it's important that we write this down. This angle can be called theta 1, and this angle in here is theta 2. Theta 1 is referred to as the angle of incidence, and theta 2 is the angle of refraction. This angle is the angle of incidence in the second case, and this angle is the angle of refraction in the second case. They are always measured between the line of light and the normal line. So when something refracts towards the normal, the angle of refraction is smaller than the angle of incidence. When it refracts away from the normal, the angle of refraction is greater. All right, well now we have a formula. We're going to be doing some calculations. You may have worked with this formula last year. This is called Snell's law. And it's a really complicated formula because there's so many equal signs. It says that V1 over V2, I'm going to start off here. It says V1 over V2 equals lambda 1 over lambda 2. That means the speed of the light in the first medium divided by the speed of the light in the second medium is equal to the wavelength in the first over the wavelength in the second. And there's all these ratios. By the way, this N2 over N1 is backwards intentionally. Everything else is 1 over 2. This is 2 over 1 because the bigger the value of N, the slower the light will move. I want to point out to everybody that this formula is actually what turns out to be 6 formulas. You can say sine of theta 1 over sine of theta 2 equals N2 over N1. Or you could say sine of theta 1 over sine of theta 2 equals V1 over V2. I'm not going to read all of these, but there's lots of different combinations here of putting these ratios together. Now, there's something that I didn't put in your notes that I really ought to have, but let's talk about it right now. If N is the index of refraction, which tells you how dense the medium is, and the bigger N is, the slower the light moves, because the material would be more dense, that would have to mean that N of light for a vacuum would have to be the smallest number of all of the indices of refraction. And it turns out that the index of refraction of light in a vacuum is 1.00. Every other index of refraction of light is a number bigger than that because when light leaves a vacuum and enters a more dense substance, it's going to slow down, so the density goes up. There's nothing less dense than a vacuum. By the way, the speed of the light in a vacuum is, of course, the speed of light that's on your formula sheet. One other thing I want to talk about here is that N of light in air and the speed of light in air are so close to being these numbers that we use them anyway. I don't want to look them up. I have a feeling that the index of refraction of light in air is actually something like 1.000375 or something. I can't remember, but it's very, very close to 1 because air is almost the same density as a vacuum. So from now on, whenever we're dealing with light in a vacuum or light in air, we can use these numbers. And by the way, both of these are given on your data sheet. Let's take a look now at the first example, and it's the only one. You do need an additional piece of information to be able to answer this question. And the piece of information is the index of refraction of light in diamond. And it turns out the index of refraction of yellow light in diamond is 2.42. So what do we have here? We have a ray of yellow light with a wavelength, travels from air to diamond. Okay, wait a minute. Air to diamond means that air is the first medium and diamond is the second medium. So when we talk about V1, we're talking about the speed in air. When we talk about V2, we're talking about the speed in diamond. So how are we going to find the speed of light in the diamond? Well, we can use N2 over N1 equals V1 over V2. That's off of your formula sheet. So be very careful here. N2 is the index of refraction of the light in diamond, which I'm telling you is 2.42. So we're going to have 2.42 over the index of refraction of light in the first medium, but that's air, which is 1.00, equals V1, that's the speed in air, which is 3.00 times 10 to the 8 meters per second, over V2. It's really, the physics 30 aspect of all this is all of the conceptual stuff that I've been talking about till now. Doing the calculation here is child's play. It's really pretty basic. So we're going to take our calculator and cross multiply. V2 will be 3.00 multiplied by 10 to the 8 divided by 2.42. So you get 1.24 times 10 to the 8 meters per second. All right, the second part of this is to determine the wavelength. Well, we're going to do pretty much the same thing we just did with the speed. We can say N2 over N1 equals lambda 1 over lambda 2. We're working with wavelengths here. So N2 is 2.42 over N1, which is 1.00, equals, now since this lambda 1 over lambda 2 is a ratio of two wavelengths, we can use whatever units we want. I think it said 570 nanometers, so that's what I'm going to put for lambda 1 over lambda 2. And now we're going to cross multiply and solve. So when you cross multiply, you'll take 570 multiplied by 1 divided by 2.42. And you get 236 nanometers. So the wavelength in the diamond is 236 nanometers. By the way, when I write lambda diamond equals 236, I hope you understand I'm talking about the wavelength of the light in the diamond. The diamond doesn't have a wavelength, it's the light that's in it. We take a look at C. C asks for the angle of refraction, so we're going to have to make use of sine of theta 1 over sine of theta 2 equals N2 over N1. You could certainly use V1 over V2 or lambda 1 over lambda 2 because you know all of that now. I'm going to go with N2 over N1 because I know those exact values. There's no rounding here. There's a problem though because You're told in the question that the light goes from air to diamond. And I thought I saw in the question that it was yellow light. So not that it really matters, but we'll draw it yellow. So you have a beam of light, and it's going to, of course, refract towards the normal. But what you're told, if we go back and look at this carefully, you're told that it says an angle of 30 degrees to the surface. So what does 30 degrees to the surface look like? Well, not what I drew, that's for sure. 30 degrees to the surface is that. This is the question's information to you, that this angle is 30 degrees. But the normal line is what the angle of incidence has to be measured from. So we need to do a little bit of grade 6 or 7 geometry here and take 90 degrees minus 30 to get theta 1, which means theta 1 is actually equal to 60 degrees. So we are going to have sine of 60 degrees over sine of the angle of refraction equals n2 over n1. Let's cross multiply first and get 1 times sine of 60, which is sine of 60, equals 2.42 sine of theta 2. So what are we going to have to do to get theta 2? I guess we're going to have to divide by 2.42 and then take the inverse sine. Remembering, of course, to be in degrees. So sine of 60, make sure you close the brackets on that 60 degrees, divided by 2.42. This is the sine of theta 2. So the inverse sine is, let's just call it 21.0 degrees. Theta 2 equals 21.0 degrees. The last two questions ask for the frequency in air and the frequency in diamond. Now, frequency doesn't appear in your refraction formula, but we do have the universal wave equation. Now, if you're going to use this to find the frequency in air, you would have to understand that the frequency in air would be the speed of light in air over the wavelength in air. If you use that formula to find the frequency in diamond, you would have to take the speed in diamond over the wavelength in diamond. But we've learned that frequency doesn't change. And I'm going to tell you right now that if you take, well, let's calculate it. Let's take the speed of light in air, which is 3 multiplied by 10 to the 8 meters per second, and divide by the wavelength in air, which was 570 nanometers, which works out to 5.7 times 10 to the negative 7 meters. I'm going to tell you right now that whatever you get for the frequency with that calculation is going to match exactly the frequency you get if you did this calculation in E, as long as you carried all your decimals from the other steps. So we don't need to do a second calculation for E. All we need to do is calculate the frequency of the light in the air. 3 multiplied by 10 to the 8 divided by 5.7 times 10 to the negative 7. I'm just going to hit enter and then show you that we could have divided by 570, and since it's nano, put negative 9 for a power on the exponent. You get the same thing. Anyway, the answer to the question is 5.26 multiplied by 10 to the 14 hertz. And that's the answer to both D and E. And that's it for the lesson. Now, before I get to your assignment, I'm just going to insert in here a short video of a couple of other demonstrations, they're very, very interesting demonstrations, and I wanted to show them to you. Okay, I'd like to share with you a couple of demonstrations. What we're looking at on the left is a beaker filled with mineral oil. And inside of the mineral oil, there's a test tube. You can see the test tube is floating right now because it's full of air. If I were to take that test tube and break it up into pieces and put all of those broken pieces of glass inside of the beaker, they would all settle to the bottom. But the question I want to discuss with you is the following. Why can we see the test tube through the side of the beaker? And it's a very interesting question that you don't even really think there's an answer to it, but there is an answer to it. Let me talk about the index of refraction of the following materials. The index of refraction of the beaker, the index of refraction of the mineral oil, and the index of refraction of the test tube. All three of those materials have the same index of refraction, which means that when light passes from glass through mineral oil, back through glass and to your eyes, you don't perceive a change in the direction of light because refraction doesn't happen. Refraction only happens when the index of refraction is different from medium to medium. But inside of the test tube, there is a column of air, and the index of refraction of air is different than the indices of refraction of all of the other materials. And that's essentially why you can see the test tube. It's not that you can see the test tube, you can see the light refracting around the air. And if I were to push that test tube down a little bit to fill that test tube with mineral oil, a very interesting thing happens. The test tube seems to disappear. Now we know that it didn't disappear, it's in there. In fact, before I started, there was already a test tube in there. There was this test tube that was in there and the test tube that I put in there. So there already was a test tube inside of there. I'll do that one more time. You can see the test tube because it's full of air. So again, the explanation is that what you're really just looking at is you're looking at the air. If I remove the air from that and replace it with a material that has the same index of refraction of its surroundings, then you can't see it. On the right, what we have is a glass of water. Now, it isn't actually a glass of water. What it contains is a whole bunch of spheres. And these spheres started off as little tiny, tiny, tiny solid plastic lumps. And when you put them in the glass of water overnight, they absorb the water, effectively becoming a sphere of water. And the index of refraction of the sphere is the same as the water. So if I take one of these and I dip it into the water, it disappears. And there are lots in there. The whole glass is full of them. So I wanted to show you those two demonstrations because I think they're just kind of interesting to look at. Okay, so I hope you enjoyed that lesson. I hope you enjoyed the demonstrations. I hope the demonstrations helped you out, at least in terms of what it means to say light refracts a particular way. On the following page, there are 9 questions that you can work on. The point I'm making here, the note, is that if I said to you, what is the speed of light in water, and you knew that the index of refraction of light in water was 1.33, you can always assume it went from air to water. You don't always have to be told that information. So I hope you have a great rest of the day. Tomorrow is a Google Hangout day, so please, if you have any questions or you need any help, come talk to me there. And if you can't make it, then send me an email. But remember, I'm here for you. If you need any help, get a hold of me and I will do my best to help you out. Enjoy the rest of your day, you guys. I'll talk with you soon.